This video features technology-enhanced items for the chemistry SOL test. Number 1. This table shows experimentally determined density values for a certain chemical. What is the percent error if the actual density is 2.02 grams per milliliter? So the first thing we have to do is calculate the average density from these three trials. So the average density would be 1.87 plus 1.94 plus 1.92 divided by 3. And that average works out to be 1.91 grams per milliliter. Now that is our experimental value. The accepted value for the density is 2.02 grams per milliliter. So the percent error, we take the accepted value, 2.02, minus the experimental value, 1.91, divided by the accepted value, 2.02. So we have a difference of 0.11 divided by 2.02 and then times 100. So that math gives us 5.4% error. And the correct answer is C, 5.4%. Number 2 is a question about significant figures. We know that density is mass divided by volume. So in this particular table, we're not going to use molar mass, but mass in grams has 4 significant figures, and volume in milliliters has 3 significant figures. If we do mass divided by volume, we have to round off our answer for density to 3 significant figures. So the correct answer is D. Number 3. Calculate the atomic mass of the theoretical element using the data in the table. Your answer must be rounded to the nearest tenth. So the way we solve a problem like this is that we have to take an average mass. This is a weighted average. We don't just take 10 plus 11 plus 13 and divide by 3. We're doing a weighted average. So for the mass number of 10, that has a relative abundance of 92%. So the math we're doing is 10 times 0.92, which is 92% as a decimal. And we get 9.2. And then we keep going for mass number 11 and mass number 13. So for the mass number 11, it's going to be multiplied by 0.065. That's 6.5% as a decimal. And we get 0.715. And then for mass number 13, we multiply by 0.015. And we get 0.195. Now, to get the average atomic mass from these three numbers, we just add them up. So 9.2 plus 0.715 plus 0.195. That total is 10.11. Now it says your answer must be rounded to the nearest tenth. So when we type our answer in the box, it gets entered as 10.1. In this question, number 4, all 4 of these samples of sulfur have the same number of protons and electrons. The only difference is the number of neutrons. So the correct answer here is that A, different isotopes of sulfur have different numbers of neutrons. Number 5. Which element has atoms that most likely have the greatest shielding effect? The shielding effect is related to electrons that are shielded from the nucleus. The farther the electrons are away from the nucleus, the more they experience this effect. So we're looking for whichever atom has the largest atomic radius, whose valence electrons are the farthest from the nucleus. On the periodic table, we can find barium, strontium, calcium, and magnesium. These are all located in the same family, group 2, the alkaline earth metals. But since size, atomic radius, increases as you go down from top to bottom, The correct answer to this question is barium, because it has the largest atomic radius and the electrons experience the greatest shielding effect. In number 6, we have to write the orbital notation for silicon at the ground state. So silicon has the symbol Si, and because it has atomic number 14, we need 14 electrons. So if we drag the first 2 electrons into the 1s sublevel, the next 2 electrons go into the 2s sublevel. That's beryllium right now. We're trying to get to silicon. This would be boron, carbon, nitrogen. So we are obeying the Pauli exclusion principle by putting the arrows with opposite spin in the same orbital. And we're obeying Hund's rule by putting a single electron in the up arrow position in separate p orbitals. So now we double up. This would be oxygen, fluorine, and neon. So we've obeyed the Pauli exclusion principle by having 2 electrons with opposite spins in the same orbital. We obeyed Hund's rule by putting 1 electron in separate orbitals on the same sublevel before doubling up. Now we're going to obey the Aufbau principle and put the next available electron into the lowest empty orbital. This would be sodium and magnesium. So we're up to a total of 12. We're trying to get to 14. That would be aluminum. And then finally silicon. Again, obeying Hund's rule. So that orbital notation diagram is now correct for silicon. In number 7, we have to write the electron configuration for argon. So argon has the symbol Ar and has a total of 18 electrons. So we're going to drag the numbers as superscripts into the proper locations. So argon is 1s2, 2s2, 2p6. If we stop right now, that would be neon. That's 10 electrons. So we keep going. 3s2. Now we're up to magnesium. And then finally 3p6. So that is the electron configuration for argon. And it says some boxes may be empty. So we don't have to do anything with the 4s, just leave it blank. And that configuration, 1s2, 2s2, 2p6, 3s2, 3p6, is correct for argon. Number 8, what is the oxidation number of a fluoride ion? So fluoride would be the ion that carries a -1 charge. So fluorine is a halogen in group 17. So because the fluoride ion contains a -1 charge, we just type -1 into the box. Number 9. How many electrons are needed to completely fill the orbitals from 1s to 4p? So if we take a look at this diagram, and we fill 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p, then these are the orbitals that will contain electrons. We can count 2 electrons for every s orbital, 6 electrons for every p orbital, and 10 electrons for every d orbital. And these will be completely full. So we have 2, 4, 6, 8 for the s orbitals. 6 times 3 is 18. 8 plus 18 is 26. And then plus 10 for the 3d. That's 36 electrons altogether. Now there is an easier way to do this. If we fill all the orbitals up through 4p, we would be in the 4th row, at the end of the p block, That's krypton. Again, 36 electrons would fill all the orbitals up through 4p. So all we have to do is type in 36 into the box. Number 10 is a bit of a tricky question. They want to know the electron configuration of scandium in scandium nitrate. So if we focus on just finding scandium in the periodic table, scandium has a total of 21 electrons, and the ground state electron configuration would correspond to A. However, that's scandium, the atom, not scandium, the ion, as found in this compound, scandium nitrate. So when scandium forms a +3 charge, which it does in scandium nitrate, it's going to lose 3 electrons. It's going to have the same configuration as argon, which is 18, not 21. So the correct answer has to do with the scandium ion with a +3 charge, and that's 18 electrons. Correct answer is B. Number 11 says, select the column in which all elements exist as diatomic molecules at room temperature. Examples of diatomic elements include hydrogen, nitrogen, oxygen, and all the halogens, fluorine, chlorine, bromine, and iodine. So the correct answer would be this particular column, which shows fluorine, chlorine, bromine, and iodine. They're all diatomic molecules at room temperature. Number 12, we have the formula for a compound, PbO2, which contains lead and oxygen, and we have to give it a name. Now, lead is a metal, and oxygen is a nonmetal. It's an ionic compound, and even though lead is not a transition metal, it still has multiple oxidation states. Sometimes it's +2, and sometimes it's +4. And you can see Roman numeral 2 and Roman numeral 4. Now we're going to use Roman numeral 4 in this case because each oxygen is worth -2, and we have 2 of them. So the charge on lead is +4. The rest of the name is just the word oxide. We don't use prefixes with ionic compounds. So the correct answer is lead, Roman numeral 4, oxide. In number 13, we have to balance this equation. There are 2 aluminums on the right, so we'll drag a 2 into this box. There are 2 irons on the left, so we'll drag a 2 over here. Normally that would be it, except it says each box must have a coefficient. So we have to go ahead and put 1s into the boxes where a 1 would normally be understood. So the coefficients from left to right are 2, 1, 1, and 2. That's it. Number 14 says, what is the molecular formula of a compound with a molar mass of 92 grams per mole and an empirical formula of NO2? Let's focus on the NO2. Nitrogen weighs around 14, oxygen weighs around 16. So if we have NO2, that's 14 plus 32, that's 46. So again, 14 for nitrogen plus 32 for the 2 oxygens, it's 46. 92 is the actual molar mass. So 92 divided by 46 equals 2. Therefore, our molecular formula is exactly twice as much as our empirical formula. So the correct answer is not NO2, but twice as much, N2O4. In number 15, the directions say to select all the correct answers. A change in which of these could affect the chemical equilibrium of a closed system? Everything would affect the chemical equilibrium of a closed system except for the catalyst. So concentration, pressure, volume, and temperature, all 4 of those should be selected. All 4 of these would affect the chemical equilibrium, causing it to shift either to the left or the right. In number 16, it says excess oxygen gas, O2, reacts with 244 grams of iron, Fe, to produce 332 grams of iron oxide, Fe2O3. What is the percent yield? First, we have to write a balanced chemical equation. Then, we need to convert 244 grams of iron into grams of Fe2O3, the product. And then finally, we need to take 332 grams, which is the actual yield, and divide that by the theoretical yield, and times 100. So first we're going to write a balanced chemical equation. So we start with iron. It reacts with oxygen, O2, and it produces the product Fe2O3. Now we have 2 oxygens on the left and 3 oxygens on the right. So we'll put coefficients of 3 and 2 so we can get 6 oxygens on each side. But now we have 4 irons on the right, so we add a 4, and the equation is balanced. Now we are going to do a grams to grams conversion, starting with 244 grams of iron. The periodic table is our first step. So 1 mole of iron weighs 55.85 grams, so we go from grams to moles. The coefficients are the second step. So moles of iron on the bottom, moles of Fe2O3 on the top, and that ratio is 2/4. The periodic table is our third step. So the total mass of Fe2O3, if we add up 2 irons and 3 oxygens, that works out to be 159.7 grams of Fe2O3 per mole. So 244 divided by 55.85 times 2 divided by 4 times 159.7, that gives us our theoretical yield. 349 grams is supposed to be produced, but in the lab, they got 332 grams of Fe2O3. So the percent yield in this experiment is the actual yield from the lab divided by the theoretical yield. So 332 divided by 349 gives us a percent yield of 95.1. So our correct answer after doing that math is B, 95.1%. Number 17. What mass of NH3 will yield 147 grams of water when this reaction goes to completion? So we have to convert 147 grams of water into grams of NH3. So first we're going to start with 147 grams of water. We'll do a periodic table step first. So the periodic table tells us that there are 18.016 grams of water for every 1 mole. Then we use the coefficients, and we're trying to get to NH3. That's going to be 2 moles of NH3 for every 1 mole of water, based on the coefficients in the balanced equation. Now we go back to the periodic table, and if we add up nitrogen and 3 hydrogens, we get 17.034 grams of NH3 for every 1 mole. So 147 divided by 18.016 times 2 times 17.034, that gives us 278 grams of NH3. So the correct answer is B, 278 grams. In number 18, which is the best estimate of the pH of a solution that has a hydroxide ion concentration of 1.25 times 10 to the negative 5 moles per liter? So first, we're going to take the negative log of the hydroxide concentration, and that will get us the pOH. And then we do 14 minus the pOH value to get us the pH. So we're going to pick up our calculator and do the following math. We take the negative logarithm, that's the log base 10 of the number 1.25 times 10 to the negative 5. If we do this on our calculator, we get that the pOH is 4.903, but that's not the correct answer. We still have to get the pH. You should know that pOH plus pH equals 14. So therefore, we have one more step. 14 minus 4.903 gives us the correct answer. So 9.097 is what we get. And so the correct answer is C, 9.097. Number 19. What change in volume occurs for 50 milliliters of a gas in a sealed container if the pressure is doubled? We should know that pressure and volume are inversely related. So if we double the pressure on a sample of gas, then the volume decreases by a factor of 2. All right, this is question 20. Directions. Plot a point on the grid. Line segments will connect the points. Plot 2 points to form a line from the data set that correctly shows the relationship between volume and moles of an ideal gas at STP. Now you have learned that 1 mole of a gas at STP has a volume of 22.4 liters. So therefore data set A is not possible. That's incorrect because it says 1.1 moles but only 12 liters. B is also not correct. 1.9 moles, 12 liters. So if I multiply 22.4 times half a mole, so 0.5, I get a volume of 11.2 liters. So 12 liters, that's not great, but that's close enough. It's the best of the 3 choices. If I take 22.4 and I multiply by 0.7 moles, that volume works out to be around 15.7. But again, 15 is the choice. It's close enough. We'll have to go with it. So on the graph, we're going to take 0.5 and 12 and make a click. That's our first point. And then we go to 15 and 0.7. So right here, that's all we had to do. Number 21, we are given data for heat of fusion and heat of vaporization. Applying 7.80 kilojoules of heat melts what mass of solid CH2Cl2 at its melting point? So we're going to have to convert 7.80 kilojoules into moles using the heat of fusion, which is melting. Then we have to convert from moles into grams using the periodic table for the molar mass of CH2Cl2. So we'll start with the number we're given, 7.80 kilojoules of heat. And again, this is melting, so we use 4.60 kilojoules per mole, but we have to put kilojoules on the bottom and 1 mole on top. Now, we're going to use the periodic table. So carbon and 2 hydrogens and 2 chlorines, that total molar mass works out to be 84.926 grams of CH2Cl2 per mole. So the math we're doing to go from kilojoules all the way to grams is 7.80 divided by 4.60 times 84.926. And if we do this math, we get 144 grams of CH2Cl2. And so the correct answer to this question is C, 144 grams. Number 22, which of these are organic compounds? You should know, for the SOL test, when they say organic compound, they mean a compound that contains at least 1 carbon atom. So the first structure is organic. The second one is not, because there's no carbon. The third one and the fourth one are organic because they each contain carbon, but neither of these last 2 structures do. So the correct answer is, I've clicked the first and the third and the fourth box, and that's it. Those are all organic. Number 23. Which formula represents a molecule with fully saturated carbon atoms? The word saturated as it applies to carbon molecules is that there are only single bonds present. So the correct answer is C. A, B, and D all contain at least one double bond. So as long as there is a double or a triple bond, that's considered unsaturated. But fully saturated means all single bonds. Number 24 is about molecular geometry. CH4, which is called methane, has a tetrahedral shape. So the best representation of that tetrahedral geometry is choice C. Number 25. Select 3 of the carbon atoms that make this molecule unsaturated. Looking for double or triple bonds. So these 3 carbons would be correct. I could also use this carbon if I wanted to, or either of these carbons. As long as it's part of either a double or a triple bond, then that would be what makes the molecule unsaturated. Number 26 is talking about polymers. We should know the difference between a synthetic polymer and a natural polymer. Synthetic polymers include things like plastics, nylon, polyester, Teflon. Natural polymers are things like carbohydrates, protein, and DNA. So naturally occurring polymers would be protein and DNA. That's the answer to this question. 7 is talking about the difference between plastics and nucleic acids. So plastics are examples of polymers that are synthetic. DNA, nucleic acids, are examples of polymers that are naturally occurring. So the correct answer is that plastics are synthetic polymers, but nucleic acids are natural polymers. Alright, well that is the end of the Chemistry Technology Enhanced items. I hope that was helpful. Thanks for watching.